Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto, and I'm the Technical Sales Director for AFT. And today I'm going to be hosting the webinar called Pulsation Control. Previously, we talked about PFA, the new release, and how you can use it for the decide stage. This is more of how solving a field problem or vibration that you might have in the field. If you have any questions during the presentation, just type it down in the chat box of GoToMeeting, and we'll answer at the end. Also, this webinar is being recorded, and in the handouts, you will find a copy of the PDF of the presentation we're giving today. So let's start with the introduction. So one of the key elements to solve a vibration problem is to determine whether the source of a high vibration displacements is due to acoustical or mechanical resonance. It's important to determine which type of resonance you're having. This is due to the fact that depending on the type of source, the type of solution varies. If you apply a mechanical solution to an acoustical problem or an acoustical solution to a mechanical problem, most probably the problem will not be solved. So you cannot change supports if you have acoustical resonance, because changing the location of the support is an external solution, and when you need an internal solution. On the other hand, you might have resonance, mechanical resonance, and it's more appropriate to have an external solution, like changing the rigidness of the support or the type of support you're using, instead of trying to solve it internally. So again, this is the basic thing. You have to determine whether you have an acoustical or mechanical problem. So talking about a little bit of the fundamental of pulsation, pressure pulsation can lead to cavitation, fatigue, pipe failures, reduction of efficiency and capacity limitation. PFA module uses digital simulation to calculate the acoustical behavior of the liquid in the piping system. With acoustical simulation, the system can be optimized from a dynamic point of view in such a way that problems caused by pressure pulsation can be minimized or avoided. Pressure pulsations propagate through the piping system at the speed of sound. Speed of sound depends on fluid bulk modulus and the pipe material and diameter. Also, the way the pipe is supported, where it's buried or not, it's also influences the speed of sound. Pressure flow pulsations reflect a geometrical discontinuity. So anytime you have valves or a change of diameters, there will be a reflection of the wave in that section. Wave reflections and wave interaction results in system acoustical natural frequencies. So depending on, that is why it's important to model properly the location when you do the location of any discontinuity in the pipe when you're going to do an acoustical analysis. System will show an acoustical response to an acoustical excitation. So not all the frequencies, we're going to see that we're going to calculate some natural acoustical frequencies. Well, not all the frequency will show, and it will depend on the acoustical response of the system, depending on the acoustical excitation you're applying. Acoustical excitation may result in acoustical resonance. The phenomenon takes place when the return of the reflective pressure wave generated by a periodic excitation coincides with the generation of pressure pulsation. The amplitude of the vibration responses can be amplified 2.5 times or higher or near a component natural critical resonance frequency. So if you have acoustical resonance in one of the acoustical natural frequencies of the system, it can be amplified up to more than 2.5 times. The stronger the excitation force, And or the closer these exciting forces are to natural frequencies, the greater the vibration amplitude will be. Now, API 74 shows the importance of the acoustical analysis, and it's reflected in its standard. So let's see a problem, theoretical problems that we're having. We have a compressor here on this side, and we're going to analyze the discharge of the compressor. So in the field, we have high vibrational problems in pipe P12. This is where we are observing high vibrational problems. So we measure them, and we go to the field and we measure them, and we see that the highest vibrations that we show are at 16 hertz, 33 hertz, 49 hertz, 66 hertz, 83 hertz, and 99 hertz. These are the frequencies that are the main frequencies that are driving all the high displacements that we are observing in pipe 12. So the first thing that we do is we build an acoustical model, and for that we're going to use Impulse with the PFA module. This is an example of the model. So and later on, when I finish the PowerPoint presentation, I'll be opening the models and going through details in each one of them. So now, once we do the frequency analysis, we graph, and we see that we see 16 hertz of acoustical natural frequency. We also see 33 hertz of acoustical natural frequency. We see, well, not so much 50 hertz, it's a small one, but here we see 99 hertz. So after doing the acoustical analysis, we conclude vibrations peak 16, 33 hertz, 49, 66 hertz, and 99 are most probably due to high shaking forces as a result of an acoustical resonant condition. Vibration 83 hertz must be result, and we didn't see it in the acoustical analysis, must be result of a mechanical resonance or high pulsation forces without resonance, or which is due to a compressor bottle sizing problem. So if you do the mechanical analysis and the acoustical analysis and you don't see any of the frequencies, most probably you will have to resize your bottle in the compressor and the PD pump. So after that, we come here, and in the step 3, we build a model using a pipe stress program. In this case, we're using Caesar 2, and we do a modal analysis. So in the modal analysis, we see that at 34 hertz, we also see the frequency 48 hertz, very close, 84 hertz, and 98 hertz. So when you do the mechanical analysis using a pipe stress program, we conclude that the high vibration due to 33 hertz is most probably due to a mechanical nature. High vibrations due to 16 hertz is most probably of acoustical nature because it didn't show up in the mechanical. And the vibration of 33, 99, 66, 66 and 99 are both mechanical and acoustical nature. So once we detect whether or not we have a problem of acoustical nature or mechanical nature, then we proceed to do an acoustical solution or a mechanical solution. So most acoustical solutions frequently advise modifications are installation of orifice plates, increasing the diameter of the pipe or the parts, relocating closed valves, or installing additional volumes. That is most frequent acoustical solution. Regarding mechanical solutions, Frequently advised modifications is the installation of additional supports, relocating or improving the quality of the supports. Sometimes, like using U-bolts, in U-bolts do not constitute a dynamic restraint. So generally, if you're using U-bolts in a pipe that has dynamic problems, most probably you have to change them because it's not they don't provide a dynamic restraint, and so the low frequency show, which are generally the ones that require less energy to vibrate. And another one would be increasing the stiffness of the structure. Sometimes the supports are not strong enough, and although they're supporting the pipe dynamically, they cannot restrain it. So these are the solutions that you might find either for acoustical or mechanical problems. So I'm going to open a, wait, let me open again the presentation. Now you have to keep in mind several things before you the quality of the analysis. Accuracy of the prediction of acoustical natural frequency is relatively good. The margin is very small, and it's plus or minus 5%. Errors controlled by limited parameters: geometry, speed of sound, compressors. So in conclusion, acoustical solutions based on acoustical model are most likely to be effective due to the precision of the acoustical models. Now, accuracy of the predictions of mechanical natural frequency is relatively low. The margin of error is around 10 or 20%, and that is due to the fact that there are many parameters that limit the accuracy of the model, which is modeling boundary conditions, modeling of rack structures, support clearance, support lift, support settling, support stiffness of clamps and restraints, friction, nonlinear supports, like uncertainty in masses, differences. So you have all these variables that can affect your model. That is why the margin of error of calculating the mechanical natural frequency is so high. So keep that in mind when you do a solution, either when you do a mechanical solution instead of acoustical solution. Conclusions: mechanical solution based on mechanical models are most likely not to be effective due to the imprecision of the mechanical models. So I'm going to open AFT Impulse and see the model. So this is the model we're building. This is the discharge of the compressor. The discharge, and we want to analyze the natural frequency, especially when we want to see pipe 12. So the first step you have to do is, in the analysis, you go to pulsation setup, and what PFA does is it hits internally with a high change, it hits internally the pipe to see the acoustical natural frequency of the whole system. So first you tell it where you're going to apply it, which is junction 2, where the compressor is located at. Then you put the properties of the pulsation source. Then you put another thing you have to do is then you go to PD pump settings, and you put the properties of your PD pump. Here we're talking about 100 RPMs, and you put the bore, the stroke, the rod length, the clearance, the suction pressure of the PD pump. if you don't have if you have an acoustical high vibration and you still want to do an acoustical analysis, it doesn't have to be a PD pump. It can be, you can just specify other instead, and it will still hit the pipe, but it will not model it as a PD pump. So no, once you do that, then you go back and you go to section pipe modeling and you check the internal strike you're going to give to the pipe, and here it is. So it's going to hit the pipe internally, the system right here, to determine the natural frequency of the system. So if I check where the compressor, the PD pump is, we go to transient, and this is here's the strike it's going to give the pipe right here in this section. And then once you do the modeling, you go to the graph result, and you have a new tab, which is frequency analysis. So here, the new tab, frequency analysis. So you go and you see the sections of pipe. In this case, we have a simple model, and but generally in the field, you'll have more than one pipe having problems. So here we selected the pipe that we want to observe and calculate the natural frequency. You can select more than one and see and compare what you measure in the field. And now, once you do that, then you generate the files, and then you go and see where here are all the natural frequencies, acoustical natural frequency of your system for pipe 12. Okay, each pipe will have different natural frequency. It doesn't mean that all the frequency are going to show. So what you do is you go and you select a window and you say, okay, let me see this frequency. And it shows you the frequency you observed. And if it's near the ones you're measuring in the field, then you say, okay, this one might be causing me problems because it's very close to what I'm measuring in the field. So once you determine this, you can determine, okay, here, like in this case, we have 16 hertz. If we go back to the presentation to what we measure in the field, we saw that 16 hertz is one of the frequencies that we are measuring in the field, and it's just the one we're seeing in an acoustical model. So 16 hertz is probably an acoustical problem, and we have to make it disappear because it's having resonance with whatever excitation we're getting. Either it's a PD pump or another type of excitation. We also have the same for 33, that's very close, and 55 is very close to what we measure in the field, and 99 the same. So these frequencies, I have to decouple them from what we're frequency excitation, because it's making my pipe vibrate, it's causing high vibration displacements in the field. So then once you do that, then you build the model with a pipe stress program. And here it's a season model, and right here is where we have the high vibrations. So once you do that, you run it. Then you check your operating loads, you check your sustain and expansion, all according to code, and say, okay, we're okay. So now you come and do your dynamic analysis. And in this case, we're going to select modal analysis because we're only interested in the mechanical natural frequencies. And the mechanical natural frequencies, as I said when I started the presentations, are determined in how you space the supports, what type of supports you use, and the diameter of the pipe and the thickness of the pipe. So once you perform your modal analysis, and it's determining the mechanical natural frequency of the system. So then you come to the report, you go to the frequency view report, and here you have all the mechanical natural frequency of the system that, as I said, I determine, and the way you have the layout of supports and the type of pipe you're using. And here with this, you go in each one of them, you see, okay, which one am I observing in the field? So this one is one probably that it's observed in the field, and so on. So these are the frequency you have to make this, you have to decouple from the excitation you have. So this, in this case, you would you would change the spacing of the supports or the rigidity of the supports to decouple this mechanical natural frequency from the ones you're measuring in the field. So this is more or less the approach you have to have. So as I said, the first step you have to do when you have a vibration problem is determine whether it's mechanical and acoustical, and you do that by doing an acoustical model, a mechanical model, and see which ones you're measuring in the field. Once you do that, you know what type of solution you would use, an acoustical solution or a mechanical solution. So now we come to the section, the part of the sections of questions and answers. Just let me know if you have any questions. Okay, I have one question here. Okay, they're asking me the parameters I use in Caesar to analyze the modal analysis. So I come in here, and if you want the Caesar model, I can send it to you. So let's see it. So I used the sustain case as a reference for my static nonlinear supports. You can use operating if you want, and basically the cutoff frequency is 100 hertz because that's what I use 100 hertz because I measure in the field up to 100 hertz. You can generally you would go in the mechanical solutions, you would go for low frequencies because, as I said, they are the ones that require less energy, the low frequencies. And what you do is you wipe them off of the system, put in them the supports closer because they are the ones that require less energy. And they're most probably the ones that will show in the field. In this case, I took 100 hertz. You can go for lower if you measure lower frequency in the field. Let me see if there's another questions. So as I said, if you want the Caesar model or the Impulse model, I can send it to you. And if you want a trial of PFA, you're welcome. Just contact sales and we can activate a license for you. I want to thank you for joining me us today. And I really encourage acoustical modeling is very simple using PFA. And we're making big efforts to, it's kind of a hidden solution, a World Cup secret, and now you have it available to do an acoustic analysis. And as I said, it's really simple. So come on, use it, contact us and try PFA. We're really excited to have this new tool available. Before I finish, there's another question. Can you please advise what margins should we maintain between acoustical frequency and mechanical frequencies? Well, in the design stage, you can keep a margin because since there's the margin of error for the mechanical model, stress model has so many variables that increase the error. I would say around 20% or 15%, it would be a safe margin to use. But as I stated in my presentation, one of the things you should do when you do a stress model is make sure that all these parameters are as precise as you can, because there's a lot of margin of errors when you do like the linear supports, if you model the supports properly and all that to determine the mechanical frequency. In the case of the acoustical solutions, the acoustical model are more precise because there's less parameters that affect the precision of the model. Let me see something, if there's more questions. Okay, so I think in piping route, if the piping route is fixed, but we find acoustical problem, is there a solution other than installation of restrictions, orifice to a cater? Yes, like you can put dampener in the system, and that which is adding a volume to the pipe, and that would change the acoustical response of the system at that section, because so orifice is not the only solution. You can put a dampener in the system, and that will change the acoustical response of your pipe to the excitation you're having. In the case of yes, they're asking if the presentation is recorded. It is recorded, and you'll receive an email. You will receive a follow-up email with the link to the webinar, and you will be able to see the recorded webinar and if you have any questions, just send me an email. I think I answered all the questions. If I didn't, just send me an email to sales@aft.com or ronaldopinto@aft.com, and it would be a pleasure to have a conversation with you and discuss any questions that you might have. As I said, what's next? You will receive a follow-up email with the link to today's webinar. Also, you'll be receiving information of upcoming webinars, and you can download for free on the website www.aft.com. Pricing information in USA is posted in a website. International, you can contact your local channel partners. Thank you again, and hope to see you in our next webinars.